Welcome to lesson 4.6, Saving and Sharing Your Fine-Tuned Model. Overview. You've trained your model. You've evaluated it. Now comes the part that makes all of that work actually useful. In this lesson, you'll learn how to save your LoRa adapters, merge them with the base model if you need to, choose the right quantization format for your use case, and optionally publish your model to the Hugging Face Hub so anyone in the world can use it. Plan for about 20 to 30 minutes, and by the end you'll have a model you can deploy, share, or hand off to a teammate. Learning objectives. Val faza fal Here's what you'll walk away with. You'll know how to save lightweight LoRa adapters, typically 50 to 200 megabytes, and how to merge those adapters into the full base model when you need a single standalone file. You'll understand the trade-offs between 4-bit, 8-bit, 16-bit, and full 32-bit formats. You'll be able to upload your model to the Hugging Face Hub, load it back for inference, write a proper model card, and make an informed decision about file sizes and deployment targets. Saving options overview. Before writing a single line of code, it's worth understanding what your options actually are, because the right choice depends entirely on what you're trying to do next. LoRa adapters alone weigh in at roughly 50 to 200 megabytes, load fast, and are the most common choice for development and sharing. A merged 4-bit model lands around 2 to 3 gigabytes and is optimized for deployment, fast inference, single file. Merged 16-bit gives you 6 to 7 gigabytes and full precision, which you'd want if you're planning to continue training. Full 32-bit pushes 12 to 14 gigabytes, maximum fidelity, but rarely necessary outside of research. The default recommendation: save your LoRa adapters. They are small, fast to upload, and trivially easy to share. Option 1. Save LoRa adapters. Recommended. The adapter-only approach has a compelling set of advantages. File sizes stay between 50 and 200 megabytes versus 6 gigabytes or more for a full merged model. Uploads and downloads are fast. You can version your adapters independently and swap them onto any compatible base model without retraining from scratch. The one trade-off: loading requires 2 steps. You load the base model first, then layer the adapter on top. For most workflows, that's a completely acceptable cost. Saving your model comes down to 2 lines. You call model.save underscore pre-prenamed with your output directory, and that writes the LoRa adapter weights, the specific parameters your training session produced, to disk. Then tokenizer.save underscore pre-prenamed writes the tokenizer alongside it, so whoever loads this model later gets everything they need in one place. The adapter weights are what encode every adaptation your model learned. Without them, you just have the original base model. With them, you have your fine-tuned version, preserved and portable. After saving, your output directory will contain a handful of files, each with a specific job. The adapter underscore model.safetenses file is the heart of it. That's your LoRa weights, typically 50 to 200 megabytes. The adapter underscore config.json tells any loader how to interpret those weights, the rank, the target modules, all the structural details. The tokenizer.json and tokenizer underscore config.json handle text encoding and decoding, and optionally, you'll add a readme.md. We'll cover that shortly. The structure is intentionally minimal, which is exactly what makes it so easy to share. This utility function walks your output directory, prints the name and size of every file it finds, and reports the total. When you run it, you're looking for a total in the range of 50 to 200 megabytes for a healthy LoRa save. If you see something dramatically larger, the adapter may have been saved with unnecessary full precision layers. If the directory is nearly empty, the save likely didn't complete. A number like 85.4 MB is exactly what you want. Compact, self-contained and ready to share. Loading your saved model back is a mirror image of saving it. You call fastlanguagemodel.fr underscore pre-trained with the local path, in this case model / my underscore first underscore LoRa, and unsloth handles the two-step process automatically. It loads the base model from your local cache, then applies your LoRa adapter weights on top. The max underscore sec underscore length of 2048 matches what you used during training, and load underscore in underscore 4-bit keeps memory usage efficient. Once loaded, for underscore inference switches the model into a fast path mode that disables gradient. The confirmation message tells you the model is live and ready to generate. Option 2. Merge LoRa with base model. Merging folds your adapter weights permanently into the base model, producing a single standalone file. The upside: no two-step loading, marginally faster inference, and full compatibility with any framework that supports the model architecture. No LoRa dependency required. The downside: file sizes jump into the gigabyte range, and uploads take correspondingly longer. This is the right choice when you're shipping to production or handing off to a team that doesn't want to manage adapter files separately. The save underscore pre-trained underscore merged method does exactly what the name suggests. It fuses your LoRa adapter weights into the base model's weight matrices and writes the result to disk as a single cohesive model. Setting save underscore method to merged underscore 16-bit preserves full 16-bit floating point precision, which means no quantization loss. The trade-off is size. Expect 6 to 7. This format is the right choice when you need maximum output quality or when you plan to continue training from this checkpoint later. Setting save underscore method to merged underscore 4-bit applies post-training quantization during the merge, compressing the model's weights to 4-bit representation. The result lands around 2 to 3 gigabytes, roughly a 3x reduction compared to 16-bit, with only a modest quality penalty in practice. This is the format you want for production deployment: fast to load, small enough to move around, and genuinely good at inference. For most real-world applications, you won't be able to tell the difference from the full precision version. GGUF is a binary format designed specifically for llama.cpp, and it's what powers local inference tools like Ollama and LM Studio. Calling save underscore preprint underscore GGUF writes your merged model in this format to the specified directory, and the quantization underscore method parameter controls. The Q4 underscore K underscore M method is a 4-bit scheme that uses a mixed precision strategy. It applies finer quantization to the layers that matter most for output quality. The result is a file around 2 to 3 gigabytes that runs efficiently even on CPU, making it the go-to format for local deployment without a CUDA environment. Here's the full picture in one place. LoRa adapters, 85 megabytes, full quality, perfect for development and sharing. Merged 4-bit, 2 to 3 gigabytes, very good quality, ideal for deployment. Merged 16-bit, 6 to 7 gigabytes, full quality, best when you need to continue training. Merged 32-bit, 12 to 14 gigabytes, full quality, reserved for cases where maximum numerical fidelity matters. GGUF Q4 underscore K underscore M, 2 to 3 gigabytes, very good quality, the format of choice for llama.cpp and Ollama. Pick the format that matches your next step. You can always regenerate others from the same adapters. Option 3. Upload to Hugging Face Hub. Publishing to the Hugging Face Hub gives you free model hosting, built-in version control, and a permanent URL you can share with anyone. Your model becomes loadable from anywhere in the world with a single line of code. The hub also gives your work community visibility. Other practitioners can discover it, build on it, and give you feedback. For a model you've put real work into, this is almost always worth doing. Two commands get you set up. First, pip install Hugging Face-hub pulls in the CLI and the Python client. Then Hugging Face-CLI login authenticates your local environment against your Hugging Face account. You'll be prompted to paste an access token. Run this once and your credentials are cached for all future uploads. When login succeeds, you'll see a confirmation in the terminal. That's your signal that the hub is ready to accept your model. You'll need a free Hugging Face account. Create one at huggingface.co/join. Then generate an access token at huggingface.co/settings/tokens and make sure to select write permission. That write permission is what allows the CLI to create repositories and upload files on your behalf. Pushing your model to the hub is 2 lines. Model.push_to_hub takes your repository name, formatted as your username followed by the model name, along with your access token. That creates the repository if it doesn't exist and uploads all the adapter files. Tokenizer.push_to_hub does the same for the tokenizer, ensuring that anyone who loads your model gets the exact tokenizer it was trained with. When both calls complete, you'll see a URL in the output pointing to your live model page. That URL is shareable immediately. If you want to push a merged model rather than just the adapters, the process has one extra step. You first call save_prep9_merged to write the merged weights locally. Merged_16-bit here gives you full precision. Then you use HFAP's upload_folder method to push that entire directory to your hub repository. The repo_ID follows the same username/model name format, and the token authenticates the upload. When the upload finishes, you'll see the confirmation message in the output. The merged model is now hosted and accessible to anyone with the URL. A model card is the documentation that travels with your model wherever it goes. This YAML front matter at the top of your readme.md tells the hub and anyone who finds your model what language it operates in, which library powers it, what tags apply for search and filtering, and what license governs its use. The model details section is equally important. It records the base model you started from, the fine-tuning method and LoRa rank, what task the model was trained for, how many examples it saw, how long training took, and what hardware you used. For this model, that's llama-3.2-3b-instruct, LoRa rank 16, structured information extraction, 100 training examples, roughly 30 minutes on future you, and anyone else who uses this model will thank present you for writing this down. Once your model is on the hub, loading it from anywhere is identical to loading a local model. You just swap the local path for your repository ID. Unslots from _preprenate fetches the adapter weights and tokenizer on first use, then caches them locally so subsequent loads are instant. The rest of the inference pipeline is unchanged. Apply_chat_template formats your input, the model generates, and the tokenizer decodes the output. The hub is just the delivery mechanism. The model behaves exactly as it did locally. The training details section of your model card should record the numbers that actually govern training: LoRa rank 16, learning rate 2E4, batch size 4 with gradient accumulation of 2 for an effective batch size of 8. Document your final training loss and validation loss, in this case 0.65 and 0.72 respectively, because those numbers tell users how well the model converged and give a baseline for comparison if they fine-tune further. Also note any known limitations. This model was optimized for short text snippets, so performance on long or complex documents may degrade. Honest documentation like this makes your model genuinely useful to others rather than just technically available. Including a BibTeX citation block in your model card is a small gesture with real impact. It gives researchers and practitioners a clean way to credit your work if they build on it, and it signals that you take your contribution seriously. Fill in your name, the model title, the year, and the hub URL. The format here follows standard academic citation conventions. Specifying the Apache 2.0 license aligns your model with the same terms as the Llama base model it derives from. This matters for anyone who wants to use your model commercially or redistribute it. They need to know what they're allowed to do. Apache 2.0 is permissive. It allows use, modification, and distribution with attribution. Stating this clearly in your model card removes ambiguity and makes your model genuinely usable by the broader community. Loading your saved model. Your saved model. Fatto, Makekios, your saved model these techniques quickly. Loading from a local path follows the same pattern as the original model load. You're just pointing from underscore prepreened at your output directory instead of a hub repository. Unsloth reads the adapter underscore config.json to understand the LoRa structure, loads the base model from cache, applies the adapter weights from adapter underscore model.safetensors, and hands the max underscore sake underscore length of 2048 should match what you use during training, and load underscore in underscore 4-bit keeps memory usage lean. After 4 underscore inference, the model is in its fastest. Loading from the hub is structurally identical. Replace the local path with your repository ID in the format your underscore username / model name. On first load, Unsloth downloads the adapter files from the hub and caches them locally. Every subsequent load reads from that cache, making it effectively instant. The 4-bit loading and inference preparation work exactly the same way regardless of whether the weights came from disk or the network. This is the pattern your users will follow when they adopt your model. The first time you load from the hub, Unsloth downloads roughly 85 megabytes of adapter weights, fast on any reasonable connection. Every load after that reads from the local cache and is effectively instantaneous. This is one of the reasons the adapter-only format is so practical. The download overhead is minimal compared to pulling a multi-gigabyte merged model. File organization best practices. A clean directory structure pays dividends the moment you start managing more than one model. Keep a top-level models folder with named subdirectories for each variant. My underscore first underscore LoRa holds your adapter files. My underscore merged underscore 4-bit and my underscore merged underscore 16-bit. A separate outputs folder stores training checkpoints. These are your safety net if you need to roll back to an earlier training state. Your datasets folder holds training and validation data versioned alongside the models that trained on them. This separation makes it immediately clear what each directory contains and makes sharing any individual component straightforward. 2 PowerShell commands cover your backup needs. Copy item with a recurse flag makes a complete copy of your model directory, adapter weights, config files, tokenizer, everything to a backup location. Verify the backup by confirming the destination folder contains the same files as the source. Compress archive takes that same directory and packages it into a zip file, which is convenient for archiving or transferring to external storage. After running either command, spot check the output to confirm the expected files are present before treating the backup as reliable. Version management. Version your model directories the same way you'd version software. Start with project 1 underscore v1 underscore LoRa as your baseline. As you iterate, more data, better hyperparameters, refined formatting, create project 1 underscore v2 underscore LoRa and project 1 when you've converged on a version you trust, promote it to project 1 underscore final underscore LoRa. If you're deploying, generate project 1 underscore final underscore 4-bit from that final adapter. This progression gives you a complete audit trail. You can always trace which training run produced which model and roll back to any earlier version without losing work. Encode 3 things in every model directory name: the project it belongs to, the version number, and the format. LoRa 4-bit, 16-bit, GGUF. That naming convention makes the contents of a directory self-evident without opening it, which matters enormously when you're managing a dozen variants across multiple projects. Deployment considerations. For local development and experimentation, LoRa adapters are the right default. The file size is minimal, loading is fast, and you can swap between different adapters on the same base model without reloading anything heavy. This flexibility is particularly valuable when you're iterating on multiple fine-tuning experiments simultaneously. Loading for local inference is straightforward. Point from underscore preprinted at your adapter directory, set max underscore seek underscore length to match your training configuration, and enable load underscore in. The for underscore inference call at the end is important. It activates Unslaw's optimized inference kernels and disables gradient computation, which meaningfully improves generation speed. After this setup, the model is ready to process inputs exactly as it did during evaluation. For production serving, the merged 4-bit model is the better choice. There is no two-step loading. The model is a single self-contained file. Loading is faster. The serving infrastructure is simpler, and at 2 to 3 gigabytes, the model is small enough to move around without friction. The quality difference from full precision is negligible for the vast majority of inference tasks. Loading a merged model for production serving follows the same from underscore preprinted pattern. The difference is that you're pointing at the merged model directory rather than an adapter directory. There's no base model to load separately. All the weights are already fused. After for underscore inference prepares the model, it's ready to sit behind a fast API or Flask endpoint and handle requests. The serving layer is entirely decoupled from the fine-tuning process, which means your deployment infrastructure doesn't need to know anything about LoRa or Unslaw. Saving in GGUF format is the bridge between your Python training environment and the broader ecosystem of local inference tools. The save underscore preprinted underscore GGUF method merges your adapter, applies the Q4 underscore K underscore M quantization scheme, and writes a single .gguf file to the specified directory. The Q4 underscore K underscore M method is worth understanding. It uses a mixed precision 4-bit approach that allocates more precision to the weight matrices that have the greatest impact on output quality. The result is a file that llama.cpp, or llama, and LM Studio can load directly, no Python runtime required. Running your GGUF model through llama.cpp is a single command. You point the binary at your .gguf file and pass a prompt string. The model processes the prompt using your fine-tuned weights and streams the output to the terminal. This is completely independent of Python, PyTorch, and CUDA. Llama.cpp handles its own inference engine, and the GGUF format carries everything the engine needs. If the output looks correct, your model is working exactly as trained, now accessible from any environment that can run a compiled binary. Complete saving notebook. Save this notebook as notebook/03-first-training/05-save-model.ipnb to keep your project organized. Alongside this notebook consolidates the entire saving workflow into a single runnable sequence. It starts by loading your trained model and tokenizer from the most recent checkpoint, with 4-bit loading enabled for memory efficiency. It then saves the LoRa adapters and tokenizer to your output directory and prints a confirmation. A file size check follows, giving you an immediate sanity check on what was written. An optional cell merges the adapters into a 4-bit model for deployment. The notebook then tests the saved model by loading it fresh and running a quick inference pass. This is the verification step that confirms your save actually worked. Finally, an optional upload cell pushes everything to the Hugging Face hub. The closing summary prints a clean record of every path and format you saved. Saving checklist. Before you consider this lesson done, run through these verification steps. Confirm your LoRa adapters and tokenizer are saved to the output directory. Check that a readme.md model card exists alongside them, documenting your hyperparameters and at least one example input and output. Then verify the save actually worked. Load the model from disk, run an inference call, and confirm the output looks reasonable. Check the file sizes. If anything is missing or unexpectedly small, the save may have been interrupted. A model that passes all of these checks is genuinely ready to share or deploy. Key takeaways. Here's what to carry forward. LoRa adapters are your best default. Small, fast, and easy to share. Merged 4-bit is the right format for production deployment. GGUF is what you want for llama.cpp and Olama. The Hugging Face Hub gives you free hosting and version control with minimal friction. A model card isn't optional. It's what makes your model usable by anyone other than you. And back up your work regularly. Training runs take time, and adapter files are small enough that there's no excuse for losing them. Module 4 complete. That's Module 4 finished. You loaded a model with Unsloth, prepared and formatted your training data, configured the training parameters, ran your first fine-tuning job, evaluated the results, and now you've saved and shared the output. You have a working fine-tuned model, one you built from scratch on your own hardware. That's a meaningful accomplishment. What's next? Module 5 takes everything you've built and extends it into the domain of chat models. You'll learn how to handle multi-turn conversations, customize model personality through system prompts, and apply chat-specific optimizations that go beyond what a simple instruction-following model can do. The techniques get more nuanced, and the results get considerably more interesting. Additional resources. For further reading, the Hugging Face Hub documentation covers model sharing and repository management in depth. The model sharing guide walks through best practices for model cards and versioning. The GGUF format guide explains the binary structure and quantization options in detail if you want to understand what's happening under the hood. Congratulations on completing Module 4. You've built something real. Different deployment targets have genuinely different requirements, and the format you choose should match where the model is going. TensorRT excels in speed for NVIDIA-specific production environments but sacrifices portability. On NX prioritizes interoperability. It runs on a wide range of hardware and inference engines. The GGUF variants offer a strong balance across compatibility, speed, and quality, which is why they've become the standard for local inference. Hugging Face, safe tensors formats, including adapter configurations, score well on quality, and are the natural choice when you're staying within the Python ecosystem. The key insight is that no single format wins on every dimension. Pick the one that matches your deployment target, not the one with the highest average score. GGUF quantization levels represent a genuine quality versus size trade-off, and understanding the numbers helps you make an informed choice. For a 7 billion parameter model, Q2_K compresses aggressively to 2.7 gigabytes, but pays a real quality penalty. Perplexity of 12.55 is noticeably degraded. Q4_0 at 4.1 gigabytes is acceptable for most applications. Q4_K_M is the sweet spot, 4.4 gigabytes, perplexity of 5.13, and the mixed precision approach preserves quality in Q5_K_M and Q6_K improve further at the cost of larger files, while Q8_0 at 7.7 gigabytes is essentially lossless. F16 at 14.5 gigabytes is full precision, useful as a reference point, but not a GGUF deployment target. For most practical use cases, Q4_K_M. The decision tree for deployment starts with a single question: is the model ready for production? If not, iterate, more data, better hyperparameters, another training run. If yes, the next question is whether you're deploying locally or in the cloud. For local deployment, GGUF plus Ollama is the most accessible path. It runs on a laptop or desktop without a Python environment and serves inference through a local llama.cpp-compatible server. For cloud deployment, Hugging Face inference endpoints handle the infrastructure for you, while a GPU server running VLLM or TGI gives you more control over throughput and batching. The right choice depends on your scale and operational constraints, but knowing all three paths means you're never locked into one. This chart makes the storage trade-offs concrete. A 7B full FP16 model and a 7B merged BF16 model both land at 14 gigabytes. That's the cost of full precision at this parameter count. Adding a LoRa adapter to a 7B base model requires only 30 megabytes of additional storage for the adapter itself, which is why the adapter-only workflow is so compelling for development. The 7B GGUF Q4_K_M brings the deployment footprint down to 4.4 gigabytes. Scaling up to 13 billion parameters, the full model hits 26 gigabytes, but the GGUF Q4_K_M variant, these numbers are worth keeping in mind when you're deciding what to store, what to upload, and what your inference environment can realistically accommodate. The adapter output directory has a clear, minimal structure by design. The adapter_model.safetenses file, typically 10 to 100 megabytes, contains the learned weight deltas that represent everything you're fine-tuning added to the base model. The base model's own weights remain frozen and separate. The adapter only stores the differences. The adapter_config.json records the structural parameters, the LoRa rank, the alpha scaling factor, and which weight matrices in the base model the adapter targets. Stonaker files are optional in the adapter directory if you're always loading from the same base model, but including them makes the adapter self-contained and eliminates any ambiguity about which tokenizer to use. This compact structure is what makes adapter-based fine-tuning so practical for iteration and sharing. The merge and upload workflow follows a clear sequence. You start with your base model, Llama 3 2.3 in this case, and the LoRa adapter weights you trained. Calling merge underscore and underscore unload fuses those adapter weights permanently into the base model's matrices, producing a single unified model with no remaining LoRa structure. You then save that merged model with save_pre. From there, two paths diverge. You can export to GGUF for local inference tools or push directly to the Hugging Face hub with push_to_hub. The GGUF path gives you a file optimized for llama.cpp. The hub path gives you a hosted model accessible from anywhere. Both start from the same merge checkpoint. Uploading to the Hugging Face hub follows a straightforward sequence. Create your account at huggingface.co, then create a new repository, either through the web interface or the CLI. Generate a write permission access token at huggingface.co/settings/tokens and authenticate with Hugging Face Drew CLI login. For adapter uploads, call model.save_preparent to write the adapter files locally. Then push _to_hub to upload your tokenizer the same way. Finally, add your readme.md model card with the language, license, and base model tags filled in. Each of these steps is a discrete action. Work through them in order and your model will be live on the hub with a permanent shareable URL. 3 distinct loading scenarios cover the full range of post-training use cases. The LoRa-only pattern loads the base model and applies the adapter on top. The right choice when you're continuing training or running quick inference experiments and want to keep the adapters separate and swappable. The merged model pattern loads a single fuse checkpoint. This is what you want for production serving or when exporting to GGUF because there's no adapter management overhead. The GGUF local pattern uses llama.cpp directly, specifying the model file and the number of GPU layers to offload. Useful for CPU primary machines or environments where you want inference without a Python runtime. Match the loading pattern to your use case and the model will behave exactly as expected. A well-organized output folder makes the difference between a project you can hand off and one only you can navigate. The structure shown here nests everything under a named experiment folder, llama3 customer support v1 in this example. Inside, a checkpoints directory holds intermediate saves at training steps 200 and 400, giving you rollback points if the final model underperforms. The final LoRa folder contains the adapter config and safetenses weights, the canonical adapter output. The merged folder holds the fused model weights alongside the model configuration JSON, training arguments, and evaluation results live as JSON files at the top level of the experiment folder, and a readme.md documents everything. The structure scales cleanly as you add more experiments and versions. A consistent naming convention eliminates ambiguity when you're managing multiple model versions. The pattern breaks down into 4 components: the abbreviated base model name, the task domain, the dataset version prefixed with a lowercase d, and the training version prefixed with a lowercase v. Assembled, that looks like llama 33b customer support t3v2, which tells you immediately what base model was used, what the model does, which dataset iteration it trained on, and which training run produced it. Your Hugging Face repository ID follows the same convention under your username. Apply this consistently from the start, and you'll never have to open a directory to figure out what's inside it.